Hello everyone and welcome to PC Retro Tech. In this week's video I'm going to be doing a deep dive into the 3D Effects Voodoo Graphics chipset. And the card that I've chosen to use in this episode is this Diamond Monster 3D 4MB card. It's a PCI card, it has 4 megs on board, the Voodoo Graphics chipset and of course a DAC. Now this particular card is from 1997. The Voodoo Graphics chipset actually came out in 1996, but it was first used in arcade cabinets. We'll pair this card with a Pentium 233 MMX processor, because that's the same year. And the other piece of hardware that you need, of course, with one of these cards is a pass-through cable. It's a little short VGA cable, like this, and it basically goes from the 2D card in your machine through the pass-through cable into this card, the 3D card, and then you plug your monitor into this card. Now I apologise, there will be a little bit of noise in this video. We're currently experiencing a windstorm where I'm living. Not much I can do about that since I have to film on the weekends. But let's get to it and stick this into our machine and check it out. This is the machine that we're going to be putting the card into, as yellow as it is. You will have seen this on the channel before when I made the video about the AMD K6 II, but I have a Pentium 233 MMX in it right now. So let's get the cover off and get the card in. Now I've got an AGP card in there at the moment from when we did our video on the AMD K6 II, so I'm going to take that out first. And then we'll just use the next two PCI slots. And actually there's also a network card in here which we won't need. I'll just free up a slot to put the video cards into. Now I've decided to use an ET6000 for the 2D card. It doesn't really matter very much what we use because we're mostly focused on the 3D part in this episode. I'll also plug the 3D Effects Voodoo Graphics card into the very next PCI slot, and of course we'll have to connect the pass-through cable between the two, and I'll just screw in these cards. Now the pass-through cable will only go one way around. If you start with the 2D card, there's only one end of it that will plug into the VGA connector, and then the other end of the cable will only plug into this hole, leaving this connector free for your monitor. So this is very straightforward to do and to get right on the first try. So we'll plug that in and we should be off to the races. Now Windows has already detected the Senglabs ET6000 card and it's going to install that itself. Now it says there's a PCI multimedia video card and that is the 3D Effects Voodoo. So it looks like there are already drivers in the standard Windows 98. It is just ordinary Windows 98, not 2nd edition, and I know some viewers have told me that I should be using 2nd edition, but I happen to know this particular setup will work for us today, and so there's not really any panic about upgrading this machine just yet. Now my first memory of using a 3D Effects card was with the Tomb Raider series of games. So this is Tomb Raider 3, it's a CD version of the game. It does say that it supports a Pentium 166 MMX, so we should be okay there. We've got plenty of memory. The only thing that concerns me a little is that this is a 1998 game. It may be a little late for the Voodoo Graphics card, but we'll give it a try and see. It does say that it supports most major graphics cards though, so we'll soon find out about that. This is all that's in my box, just the CD. I think there's probably some manuals that are missing from there, unfortunately, from whoever owned it before I did. But let's put it in and see whether it'll run. So I'm not sure whether this will auto-run in Windows 98, but we'll find out in a second. Just give the CD drive a little bit of time to speed up. This is a 12 times drive. Yeah, it seems to be okay. And it looks like it wants to install itself, so I'll go ahead and do that and we'll give it a try. Well, fairly remarkably, it has actually detected the 3D Effects DirectX driver, the Direct 3D, and it gives some options here for 640x480 and various other resolutions. I'm certainly not going to put that any higher than it currently is. And there are some other things that we can turn off here if we have problems at all with performance. But it looks like it's going to work. Well, there doesn't seem to be any problems so far. The out-of-the-box experience here has been really remarkable. My former experience with these games is that they took a lot of effort to get installed with settings that need changing and so on, but I think that what I've done previously is use the Windows 95, and obviously Windows 98 is doing a much better job of just making this a smooth experience. So of course this is all just a video playing off the CD at the moment, and I guess we can go through to the game and things will be a little bit different. Well, I have to say that the performance here and the graphics are absolutely stunning. It's a little bit of jerking just at the start here as it loads everything, but after that it's relatively smooth. Obviously this is not a very high frame rate, but this looks absolutely stunning. And I have to say I'm a little bit surprised that a Voodoo 1 actually works quite so well with this game straight out of the box. Very, very impressive actually. Well, why were these cards able to do such an impressive job compared to a 2D card of the same era, even on such early hardware? And the answer is really due to the chipset, the Voodoo Graphics chipset on these cards. Now this is a public domain die shot of the smaller of the two chips, the 500-004-02, which is the texture mapping unit, the TMU. The other chip is called the FBI, the larger of the two, and I'll talk about that separately. You can see that there are 4 lanes in this chip, going down to 2 here, and I'll talk a little bit about the technical layout of the chip and what this actually does, because we have the technical reference manual from 3DFX, which gives a lot of detail about how these chips work. Now these chips were done on a 500 nanometer process, 500 nanometers, so half a micrometer, and as you can see they're very complex, they have a lot of transistors in them, and they're really quite powerful for the time. And this is the corresponding die shot for the larger of the two chips, the 500-0003-03, or the FBI chip, which is presumably frame buffer interface. And I want to thank Fritzchens Fritz for putting these die shots in the public domain. Check out his Flickr. He has some amazing die shots, not just of these cards, but also other graphics cards and CPUs. Really fantastic stuff. We're in a different part of Lara's mansion now, but I just wanted to talk a little bit about how these cards worked, in particular the texture mapping unit and frame buffer interface. So the way they operated is to map an image called a texture onto a polygon, in this case just triangles, and then they would compose all of that together and create a final image that would be stored in the frame buffer, which would go on the screen. Now I think you can actually see a triangle just popping out here from the background. It's not quite joined up correctly. And the texture mapping unit's job was to map the image onto that triangle. All of the work to figure out where that triangle should go in three-dimensional space has to be done by the CPU in these early cards. They were very, very primitive. Looks like the butler has come to give us some tea. So this is really just the end of a rendering process, the final stage called rasterization, which is all about putting the individual pixels, you're basically painting the image. And so the texture mapping unit is responsible for putting the textures onto the triangles, and the frame buffer interface really is just an interface to the memory of the frame buffer where the final image is going to be stored. So these cards typically had 2 megabytes for textures and 2 megabytes for the frame buffer, and basically the end result is just then converted using the DAC, the digital to analog converter, to signals to go out to a monitor. This is the 3DFX technical document, which is available online. It was written in 1999 by the looks of it. It has an interesting copyright notice. It says that I can show you the whole of this document, but I can't show you part of it. So we're going to have to skip through some pages here which we're less interested in, and I'll focus on the ones that we are interested in. So the first one that I want to talk about is just the features of the card. You can see that it has a raster engine based on triangles. It also does some shading, but this is very primitive shading. So it's not quite as simple as flat shading, where you just use the same shading value across the entire triangle. It's Gouraud shading, where you'd compute a lighting value for each corner of the triangle and then linearly interpolate across the rest of the triangle. So obviously if you had some highlight in the middle of the triangle, you'd miss that because it wasn't included in the data that was at the corners. You've just used a formula to do the shading. So it's not as sophisticated as something like Phong shading, which would give you a much better looking result, but still cool that it actually had this feature in the card. So the next thing is the Z buffer, and this is a 16-bit Z buffer, which is used to determine which triangles to show and which ones are hidden by other triangles. So in other words, it takes care of occlusion, where something is blocking something else. And this is not a particularly accurate Z buffer, it's only 16 bits. And one of the problems with these early Z buffers is that you got something called Zed Fighting. And this is where two triangles be roughly the same distance apart and occluding one another, and it couldn't decide which is actually the closer because of the precision, and so you'd end up with just random pixels from each of the two textures being displayed. So they invented something called W buffering, which is used for these old cards like this, and seems to be something that they made a major contribution to, since they've got a patent pending. And this basically just improves the precision. I won't go into the maths of it, but it deals with some of these problems that you get with low precision Z buffers. Modern cards don't need this, they have a much higher Z buffer precision. One of the problems with textures, of course, is that they have to be shown at lots of different distances. And if a texture is very far away, you have a question about which pixels should you actually show. You have to choose some of the pixels, some of the colors in that texture to show which ones should you pick. If it's very, very close, you're then going to get, individual pixels might end up being blown up into a big square, and so you get kind of weird artifacts just switching between the pixels, just be squares of different color next to each other. So there's something called filtering, which helps to smooth things out, texture filtering, and there are various different ways of doing it. Point sampling is just where you pick appropriate points. Bilinear and trilinear filtering, where you try to smooth this, all the kind of artifacts that you get from this out. Mip mapping is another trick that they use, where you actually store multiple different versions of the texture at different sizes. Each will be half the size of the previous one. And then when you go to display a picture, that has a texture, you'll pick whichever version of the texture is the most appropriate and then just scale that by a little bit instead of having to do a very large amount of scaling. And this gives you a much nicer looking result, especially with the filtering applied as well. So there's a whole bunch of different texture formats that are supplied. I won't go into those. It also supports alpha blending, which is useful if you want to have two textures, one of which is in front of another, and you want to see part of one texture and part of the other. For example, a window, and you want to see what's behind the window as well. Then you need something like alpha blending. So it's just an alpha component to which textures say how much of that texture should be displayed and how much of the one behind it should be displayed. Sub-pixel correction is just a way of dealing with any kind of linear thing that you're computing. I mean, a standard example is when you're drawing a straight line. And one way of doing this is just to pick an endpoint and pick another endpoint on the screen, and then just use a standard line drawing algorithm to draw the line between those 2 points. But now suppose that the texture is moving slightly and it drifts by a little bit less than the width of a pixel, so it doesn't actually really move to the next pixel. if you use that algorithm, you're going to end up with exactly the same line because it just didn't move by a whole pixel. And so all the points that you're going to display will be exactly the same points. Sub-pixel correction allows you to draw things that are linear like that as though you were moving them by less than a pixel at a time, and it will actually change which points end up being displayed. It'll pick the points that are closest to the true line rather than the ones that just come out of the standard line drawing algorithm. So this can improve the way images look quite a lot. Now they also have some dithering, and this is where you take multiple different colors and just sort of alternate between them to give the appearance of having more colors than you really have. There are various other tricks in here which I won't go into. Some of them I'm not even actually sure how they work. Another thing I found very interesting about this is that the bandwidth to the memory here, which is apparently dual channel, is 1 gigabyte per second, which is pretty impressive for the day. Now this is not over the PCI bus, of course, since the memory is actually on board the card. But yeah, I'm really impressed with that number. It turns out you can have up to 4 megabytes for the frame buffer and up to 4 for the texture memory, although as I said, most of these cards just picked 2 of each. And that gives you some limitations. If you just have 2 megabytes of frame buffer and you want to have these options, you're really stuck with 640-480 resolution. The next page is also an interesting one, and it gives performance figures for the card in thousands of triangles per second. And it goes all the way through from just flat shading with everything switched off, including Zed buffering, by the way, all the way through to everything switched on and very large triangles. And you can see that it starts at 1911,000 triangles per second. Really impressive for hardware of that era. Still, something like 20 times slower than, even a GeForce 256, which was really the first GPU. But still much better than a 2D card. And it goes all the way down to, 37,000 triangles per second for the largest triangles with everything switched on. We've actually already covered most of the stuff on this page already. It's just the block diagram layout of the card. It's the frame buffer interface chip, the texture mapping chip, which is called TREX here, texture mapping engine. There's the texture memory and the frame buffer memory. There's the digital to analog converter, which makes the signals for the monitor, and of course it's connected to the PCI bus. So nothing particularly interesting there. The next page says that you can basically have multiple texture engines sort of chained together to obviously give better performance. And then it sort of goes through what you can actually get if you have 1, 2 or 3 TREXs. Some of the things are not even supported with just a single TREX, and other things become 2-pass operations. Almost everything just becomes a single pass operation if you have 3 TREXs. And of course, if you really want to pay these people a lot of money, you can get 2 FBIs and 6 TREXs. The next page gives a little bit more detail on how, especially the FBI is internally. And you can see various units in here. There's dithering, alpha blending, there's a fog unit, color combining, and so on. And of course, this is the one that talks to the frame buffer. And the TREX, there's not so much detail about what's going on inside there. I don't know what all of the terminology here means, but this does give you an idea of a little bit more of the breakdown between the 2 chips and what they actually do. The rest of the document sets out in more detail what the card does and how it works. So it starts off going through each of the features and describing them, and it doesn't really say much more than what I said. There's a few more technical details. And then from there on in, it's just describing how all the registers and so on in the card actually function, which is what you would need if you were going to program the thing. It starts off by giving the address space. So it doesn't use I/O mapped memory, it uses just memory mapped address spaces. So all the registers for controlling the card are just memory addresses. And then there's the frame buffer itself, and then there's the texture memory. So this is very straightforward setup, but there are many registers, and I'm not going to go through any of this in any detail. I'm really just satisfying the requirements of showing you this entire thing. There are some neat diagrams in there explaining exactly how various things are implemented in the chip that you would need to know as a programmer. And it's a pretty long document. It's about 90-something pages, and every single register in the card is described in detail what it does. I think all documents for video cards should be written in this way. There's a section on linear frame buffer access, texture memory access, and then there's programming caveats, problems that you might encounter, and finally video timings. And then there's just a revision history. So very complete document. I'll leave a link in the description if you want to check it out yourself. Very cool to find that much detail on a card. The next thing that I want to do is to play with the detail levels in this game. There's actually options that you can turn off, which basically disable various parts of the card. And so this is what things look like just normally. And so if we go into options here, there is about 3 or 4 options we can change. Now the Zed buffer, as we said, deals with occlusion, so it's not even clear to me how the game could even work without a Zed buffer, but let's turn it off and see what the effect is. And in fact it does seem to work. I don't really notice any difference in performance here, but here we have a triangle is missing, which was there before, and this is because the occlusion thing presumably is not functioning the way it should. Now I don't know how it's actually doing this without the Zed buffer. I don't know whether it's just lowering the precision of the Zed buffer or whether it's actually turning it off altogether, and if it is, whether the drivers are compensating by doing all that in software. But at least for the moment I don't see any real performance increase by turning that off. I'm not sure that this was there either before. That looks like another defect that's come from this. So let's turn off one of the other options and see what happens. So we'll turn that back on, and instead I'm going to turn the filtering off, and this should make textures that are very close and textures that are very far away have a lot of artifacts. So let's switch that off and see how it looks. So if we, yeah, this is a big difference. Notice the jaggies now on all the corners of the tiles here because those textures are close up, and look at the artifacts in the background. Everything just looks like it's flickering because it's not doing any smoothing in the faraway textures. So this is a very obvious change, and again I don't really see any major difference in performance here. I don't think that just switching one option off like this actually makes the performance all that much higher. So let's have a look at the next option, and we'll turn that back on. This is the dithering, and the dithering should control the color. Remember, dithering gives you the appearance of having more color, so things should pop less, they should look flatter. So let's switch that off and have a look at how that appears. And yeah, to me things look kind of washed out a little bit, but also the textures just don't look as clean. They look sort of muddy and dirty now, as though they're just fewer colors in the textures. It's actually much more noticeable than I was expecting. This room doesn't pop as much. It's not as bright and cheery looking. It just looks a little bit flatter to me. I'm not sure how well that comes across on camera, but that is a noticeable effect. Again, I can't really see any major difference in performance here, so I think we have to turn multiple options off to see that. So let's see what else there is there. I think that may be pretty much it for this portion. Yeah, so true alpha we can't change. It's not a feature of this card. Obviously that's there for other cards. Gamma just changes the brightness. So if I turn that up to 10, you'll see that everything looks very bright. But otherwise it doesn't really change the card. It's not turning a feature of the card off. It's just adjusting the alpha value for the textures. So let's now switch off a number of the features altogether and see how that looks. So I'll just put this back down to a more sensible value. It can go up a little bit more than it was before. But now let's turn off everything basically, the dither, filter and the Z buffer, and see how things look now and whether there's any noticeable increase in performance. And I have to be honest, I still don't see a noticeable difference in performance. In fact, well, I think it's just loading a different area of the CD there. But yeah, I don't really notice myself any difference in performance. I think you would probably have to have you know, some kind of CPU challenge in order for this to be worthwhile doing. All it's really doing is just making the thing look very, very basic. So let's just go back to turning the options back on again, and you'll see that in fact things improve really a lot when you turn them all back on. So that's what the card does, that's what the features do. The final thing that I want to talk about today is how you could program this card. Now, I'm not actually going to do any programming in this video. That might be an interesting topic for a later video. Let me know in the comments if you'd like to see that. But instead, I'm just going to talk about the different methods that you had available to do that. So obviously the first one is you could just program the card directly via the PCI bus and you know, using those memory mapped registers that we talked about in the technical documentation. This would be the hardest way to do it, and obviously you really want a whole lot of higher level functionality on top of that, and so you're going to be working pretty hard to get anywhere, and any defects in the design of the card would have been compensated for in drivers anyway, so you really probably don't want to deal directly with the card except as an academic exercise. The second way that you can do it is using Microsoft's Direct 3D. So there'd be a software development kit that you could download for you know, programming all sorts of 3D cards through a kind of common interface. And this is actually working through the drivers. The third way that you could do it is using a kind of cut down OpenGL implementation that they came up with for the card called Minigl. And they did this because they wanted to, you know, have games like Quake run on the card. So the final way is the way that 3dfx provided themselves, and that is their Glide API, and that's what this document is about. Now, this is a very long document, much longer than the technical document, so I'm just going to go through the chapter titles and talk about what is actually in this document. So the first thing is they give a little bit of an overview of Glide, and that's similar to what we've done in this video, I would say. The next part is they sort of give a state machine model for the card itself. You know, if you put it into this state, it'll act this way, and if you put it into that state, it'll act that way, and so on. It'll talk about how you specify vertices and how numerical data is you know, how numerical data is handled. And then you have a sort of getting started guide. This is really where the meat of the first part of the description is. And this talks about the display buffer, how to write to the frame buffer, swapping buffers, clearing buffers, and so on. So this is really about just starting the thing up, shutting it down, and how to write to the frame buffer. Then you have a section on rendering primitives. So primitives are things like triangles, points, lines, polygons. It talks about backface culling, so you know, faces that are facing away from you that you don't want to see, and anti-aliasing. Then in Chapter 5, it talks about colour and lighting, how to specify colours, how to, you know, do the dithering and a gamma correction, and what the colour combine unit is all about. So then it talks about the alpha component. We showed earlier what alpha actually does, and it tells you how to specify it, how to do alpha buffering and alpha blending. And then it talks about depth buffering. So fixed point Z buffering, floating point W buffering. That was the method that they came up with to work around some of the problems with Z buffering. And basically all of that is on this topic with an example, of course. And then there are some special effects that you can apply. There's fog, chroma keying, alpha testing, and stenciling. And chapter 9 is about texture mapping. So texture mapping is obviously where you start getting into the real 3D meat, and it talks everything about filtering, Mip map blending, the trilinear filtering. LOD is level of detail, so if something's further away you don't need as much detail in the textures, and if it's close you do. So you can have the card do less work if something's further away. It just explains some basics about how texturing actually works. And then managing texture memory. So you have to load all of those textures into the texture memory so that they can be then used by the card to put on the actual objects. So I won't go through the details there. You can read those yourself easily enough. How to access the linear frame buffer, and some housekeeping utilities, and finally some glide utilities that'll help you, and a few programming tips. So this is a pretty comprehensive document. Again, very impressed. Unfortunately, I think this particular version has been scanned in using OCR, and it's not a particularly high quality rendition, I think, but all the detail is there. And yeah, this gives you a way of actually programming the card pretty much the way that 3dFX intended. So anyway, I'm going to leave it there. There may be a second part to this video at a later point if I actually get up the energy to actually do some 3dFX programming, which I think would be fun. We could put some basic primitives on the screen, rotate them around, put lighting on them, and just see what each of the different features of the card do. So let me know if you'd like to see that, but otherwise that's it for this week. Thanks as always for watching, and we'll see you in a later video. Bye!